So this time we're taking a look at section 11.10. 11.10 deals with Taylor and Maclaurin series. So we're going to start out with a function f. And we're going to suppose that f can be represented by a power series. Well, if that's the case, then that means that f of x can be written as c sub 0 plus c1 times x minus a plus c2 times the square of x minus a plus c3 times the cube of x minus a, and so forth. And we're going to assume that absolute value of x minus a is less than our radius of convergence r. But if you think about what happens if you evaluate f at a, you're going to get c0 plus c1 times a minus a, but that's going to be 0, plus c2 times the square of a minus a, which is also going to be 0, plus c3 times the cube of a minus a, which is also equal to 0. And in fact, what we notice is that this pattern is going to just continue on forever, where you're going to have a minus a raised to higher and higher powers, and you're getting 0 every time. So when we plug in a for x, all that we get is c sub 0. And in fact, what we're going to do is think about what these other coefficients would have to look like. Now, if we think about what the other coefficients would have to look like, then we need to know something about c1, c2, c3, and so forth. And one way that we could get an idea as to what's going on with c1 is to take a look at f prime of x. And so if you take a look at f prime of x, derivative of c sub 0 is 0. The derivative of c1 times x minus a will be c1. And then we'll have a 2c2 times x minus a plus a 3c3 times x minus a raised to the second power, and so forth. And here, once again, we'll have absolute value of x minus a is less than r. But if we apply the same type of technique by plugging in a this time to f prime of x, then what we see is that we're going to get c1 plus then 2c2 times a minus a, which is going to be 0, plus 3c3 times the square of a minus a, which is going to be 0, and so forth. And what that tells us is that f prime of a is going to be the same thing as c1. So now we know what c0 and c sub 1 look like. C sub 0 is f of a, c sub 1 is f prime of a. But let's think about what would happen if we wanted to figure something out about c2. Well, this time we can take a look at f double prime of x. And if we take a look at f double prime of x, we differentiate c1, we get 0. The 2c2 times x minus a differentiates to 2c2. And then we'll have a plus 3 times c3 times 2 times x minus a. Well, that'll give us a, we'll go ahead and just write it as a 3 times 2 times c3 times x minus a, so forth. And again, we'll have absolute value x minus a less than r. So now if we plug in a for x, we take a look at f double prime of a, we're going to get 2c2 plus 3 times 2 times c3 times a minus a, and that's going to be 0. And as we move on down this sum, we're always going to have x minus a raised to at least the first power. And so when you plug in a for x, all those different pieces are going to 0 out, which means that f double prime of a is 2c2, or we could say that c2 is f double prime of a divided by 2. Now we could also ask about C3, and we could play the same game that we've been playing, but I think it's probably worth taking a look at. So let's consider what f triple prime of x would look like. Now if we take the derivative of f double prime, 2c2 is going to differentiate to 0. Then we'll have a 3 times 2 times c3 when we differentiate that term. And if you think about what the next term would be, well, let's keep in mind that the next term up here with our f of x would have been c4 times x minus a raised to the 4th. And that would have differentiated to a 4c4 times x minus a raised to the 3rd. And then that would have differentiated to a 4 times 3 times c4 times x minus a squared. And then that would have differentiated to 4 times 3 times 2 times c4 times x minus a. So what we have in blue here is just the term, is the part that would follow this piece here. This would follow this piece, this would follow this piece, and then I just went ahead and wrote out what that, what the derivative of this thing would be in the representation we have for f triple prime. But notice, if we were to plug in a for x, f triple prime of a would be 3 times 2 times c3. And then you'd have 4 times 3 times 2 times c4 times a minus a, so that would zero out, and everything else beyond that would zero out when we plug in a for x. And so when you think about what c3 is, well, c3 we could write as f triple prime of a over 3 times 2, but 3 times 2 is equivalent to 3 factorial. If we were to take a look at c2 again, f double prime of a over 2, well, you could write that as f double prime of a over 2 factorial. C1, f prime of a, which you could write as f prime of a over 1 factorial. And c sub 0 is f of a, which you could write as c sub 0 is equal to f of a over 0 factorial, because 0 factorial is 1. So it looks like we have some sort of pattern that we're establishing here, to the point where c sub n we would think of as the nth derivative of f of a over n factorial. And so now we have our representation that tells us what each of these coefficients will look like. And that leads us to the following theorem. So if f has a power series representation at a, that is, you can write your f of x as follows. Summation n equals 0 to infinity, c sub n times x minus a raised to the nth power, absolute value x minus a less than r. Then its coefficients are given by c sub n equals nth derivative of f at a over n factorial. And so if you think about it, the c sub n is going to get replaced with this nth derivative of f at a over m factorial. So it'll look something like the following. So the summation n equals 0 to infinity of nth derivative of f at a over m factorial times x minus a raised to the nth power. And if you think about what the first few terms would look like, if you start with n equals 0, the 0th derivative of f at a, well, we're just thinking about that as the original function at a. Over 0 factorial, it's over 1. So you would have f of a, and then x minus a raised to the 0th power, thinking that as 1. So when you have n equals 0, plug it in, you're just getting f of a. Now if you have n equals 1, you have the first derivative of f at a over 1 factorial, so that's going to be over 1. Just go ahead and write it this way. And then it'll be times x minus a raised to the first power, or just times x minus a. Now, if you take a look at the term you get with n equals 2, you'll have second derivative of f at a over 2 factorial times x minus a raised to the second power, and this just keeps going on and on. Now, this is what we refer to as a Taylor series for the function f at a. And so, if you think about this representation, it can also be expressed as the Taylor series for f centered at a. Sometimes you hear it mentioned that way. Now, for the special case where a is equal to 0, then what we're going to get is f of x is equal to summation we're going to get summation n equals 0 to infinity of nth derivative of f at 0 over n factorial times x minus 0 raised to the n. Well, that's just going to be x to the n. And that's what we refer to as a Maclaurin series. So what you're going to get, first two terms, n equals 0, 0th derivative of f at 0, well, that's f of 0, over 0 factorial is over 1, times x to the 0 times 1. So you're going to get f of 0 as that first term. And then if n is equal to 1, you'll have first derivative of f at 0 over 1 factorial. But that's just f prime of 0, and that'll be times x to the first. And then if n is equal to 2, you'll have the second derivative of f at 0 over 2 factorial, or f double prime of 0 over 2 factorial times x squared. And so that's the sort of pattern is just going to continue. So once again, this is what we refer to as a Maclaurin series, Taylor series centered at 0. So let's take a look at how we can get Taylor and Maclaurin series for different functions. And so to do that, we're going to make a little bit of room. And then here we're going to be saying, let's find the Maclaurin series of the function. Okay, so find the Maclaurin series of the function. And the function we're going to be dealing with is f of x equals e to the x. And then we're going to find its radius of convergence. Okay, so once again, Maclaurin series, you're looking at Taylor series centered at the 0. Alright, so if we take a look at f of x equals e to the x, we're trying to find a Maclaurin series for that function, and we're going to find the radius of convergence. Now, what we have to keep in mind is that if our goal is to figure out the Maclaurin series, then what we need to do is figure out what f of 0, f prime of 0, f double prime of 0, and so forth are all equal to. So here we have f of x is equal to e to the x. But we also know that f prime of x is e to the x. F double prime of x is e to the x. And no matter how many times we decide to take the derivative, we're still going to get the same thing. So in general, the nth derivative of f of x equals e to the x is e to the x. So what this means is that if we were to take a look at evaluating each of these at x equals 0, you'd have f of 0 is e to the 0, which is 1. F prime of 0 would be e to the 0, which is 1. And we just keep getting 1 when we move down this list. Evaluate each of these derivatives at 0, and each of those derivatives is going to give you 1. So that's pretty neat, because notice that the representation that we have for the Maclaurin series is we're going to have f of x is equal to summation n equals 0 to infinity, nth derivative of f at 0 over n factorial times x to the n. But see, we know that the nth derivative of f at 0 is always going to be equal to 1. So we're going to get 1 over n factorial times x to the n as our general term, or we could just simply write it as x to the n over n factorial. So f of x is e to the x. You can write as summation n equals 0 to infinity, x to the n over n factorial. So that's our Maclaurin series for f of x equals e to the x. But we still need to figure out what the radius of convergence is. And so to figure out the radius of convergence, we go back to what we were doing a couple of sections ago when we took a look at our power series, and we figured out where those converge, which x do those converge. And so we'll use the ratio test to figure out the radius of convergence here. We'll take the limit as n approaches infinity, absolute value of a sub n plus 1 over a sub n. But let's remember that a sub n plus 1 is going to be what we get when we replace the n's in the general term with n plus 1s. So we'll have the limit as n approaches infinity. So your a sub n plus 1 is going to be x to the n plus 1 over n plus 1 factorial. Put that over a sub n. You have x to the n over n factorial. And we'll take the absolute value of that. So now we have the means to simplify this a bit. So the limit as n approaches infinity. And remember, dividing by this is the same as multiplying by its reciprocal. So you'll have your x to the n plus 1 over n plus 1 factorial times n factorial over x to the n. Now we've seen this sort of thing with the n factorial and the n plus 1 factorial quite a bit. And remember that n plus 1 factorial is the same as n factorial times n plus 1. So the n factorial that we can get out of here is going to reduce with the n factorial we have up top. We'll still have a factor of n plus 1 on the bottom. But when we simplify, what that means is we're going to have the limit as n approaches infinity. Your x to the n plus 1 over x to the n is going to give you x up top. And then we'll have the n plus 1 on the bottom. So we can think of this as the limit as n approaches infinity. 1 over n plus 1 times the absolute value of x. Now, as n grows larger and larger, 1 over n plus 1 is getting closer and closer to 0. So this limit is actually 0, no matter what real choice of x we have. So as a result, since we know that the ratio test gives us a limit that's less than 1 for every real choice of x, that means that our radius of convergence is infinity. That is, series converges for all real x. So it's a pretty nice representation that we have for e to the x, and we'll see that show up again before the end of the section. Now, let's take a look at the following. So for a Taylor series, we can take a look at partial sums. So for a Taylor series, partial sums are, we're going to call these t sub n of x. And basically, what we're going to do is we're going to take a look at the summation from I equals 0 to n of your nth derivative, or sorry, your ith derivative of f at a. So ith derivative of f at a over I factorial times x minus a raised to the ith power. So basically what we're doing is we're saying, let's take the index from 0 all the way to n, let's add all those terms together, and that'll be the partial sum that we refer to as t sub n of x. Now this is a polynomial of degree n. Once again, it's a polynomial of degree n that we call the nth degree Taylor polynomial. Nth degree Taylor polynomial of f at a. All right. So, in general, f of x is the sum of its Taylor series so f of x is the sum of its Taylor series if f of x is the limit as n approaches infinity of t sub n of x. All right. So next, let's take a look at the Taylor series. Once again, for f of x equals e to the x. But we're not going to be centering this at 0. We already did that. That was our Maclaurin series. But we're going to do it instead at x equals 2. So Taylor series for f of x equals e to the x centered at 2. All right. So if you think about what's going on here, well, when you take a look at your Taylor series centered at 2, then you're going to get the summation n equals 0 to infinity of the nth derivative of f at a over m factorial times x minus a raised to the nth power, where a is equal to 2. So this is the kind of format that we're really looking for, which means that we're going to need to know something about the nth derivative of f at 2. Well, fortunately, again, f of x equals e to the x. So we can take a look at f prime, f double prime, doesn't matter which derivative we're taking here. We're going to get e to the x. But remember, we need to evaluate these derivatives at 2. And so when we evaluate each of these at x equals 2, we're just going to be getting e to the second power. So with this in mind, if we are taking a look at putting together our Taylor series, remember, f of x, this is the form we're looking for. F of x is going to be summation n equals 0 to infinity, nth derivative of f at 2 over n factorial is x minus 2 raised to the nth power, but we know what the nth derivative of f at 2 is. It's going to be e squared. So summation n equals 0 to infinity e squared over n factorial times x minus 2 raised to the n. And this also is going to work for all real x. So you could also verify that using the ratio test if you wanted to, but I'm not going to bother with that here. Okay. So next, let's consider the Maclaurin series. And this time we're going to be looking at sine x. So Maclaurin series for sine of x. So again, if we're looking at a Maclaurin series, we're going to need to know something about our original function and its derivatives. So let's take a look. We'll have f of x is sine x, f prime of x is cosine x, f double prime of x is negative sine x, triple prime of x is negative cosine x. Fourth derivative of f at x, we're back to where we started. And so basically what we have to do, if we're going to be figuring out a Maclaurin series, is we've got to figure out what happens when x is equal to 0. And so f of 0 is equal to sine 0, which is 0. F prime of 0 is cosine 0, which is 1. F double prime of 0, negative sine 0, which is 0. F triple prime of 0 is negative cosine 0, which is negative 1. And then our fourth derivative of f is 0. Well, we're back where we started. It's going to be sine 0, which is equal to 0. And from this we can see that the fifth derivative of f at 0 will be the same as the first derivative of f at 0, which is giving 1. So these derivatives evaluated at 0, we're basically looking at a pattern where we go 0, 1, 0, negative 1, 0, 1, 0, negative 1, 0, 1, 0, negative 1, and so forth. And that pattern's just going to keep going on forever. And so we think about writing out the first few terms of the Maclaurin series for sine of x. And what we get is that sine of x is going to be f of 0 plus f prime of 0 times x plus f double prime of 0 over 2 factorial times x squared plus f triple prime of 0 over 3 factorial times x cubed, and so forth. So a lot of these terms are going to end up zeroing out. So for example, when we see our f of 0, we already know that's equal to 0. And then we'll have f prime of 0 times x. Well, that's going to be 1 times x, or just x. And then we'll have f double prime of 0 over 2 factorial times x squared. But your f double prime of 0 is 0, so this isn't going to show up. You then have an f triple prime of 0 over 3 factorial times x cubed. Well, your f triple prime of 0 is negative 1. So that means you're going to have a minus and then x cubed over 3 factorial. Now, if we were to take a look at what would follow after the f triple prime of 0 over 3 factorial times x cubed, what you would have would be fourth derivative of f at 0 over 4 factorial times x to the fourth. But we know the fourth derivative of f at 0 is equal to 0, so this wouldn't even show up. And then we would have plus fifth derivative of f at 0 over 5 factorial times x to the fifth. But if you think about the fifth derivative at 0, that would be the same as the first derivative at 0, and that's 1. So you're going to have a plus 1 over 5 factorial times x to the fifth. And that will give you x to the fifth over 5 factorial. And what you may notice is that there's a pattern that's starting to emerge. Notice we don't see any even powers of x showing up. But we do have an x to the first, we have a minus x to the third over 3 factorial, we have a plus x to the fifth over 5 factorial. And so following this pattern, you might think that the next term is going to be a minus x to the seventh over 7 factorial. And if that's what you think, then good, because you're right. And then the next term will be a plus x to the ninth over 9 factorial. When I say next term, I mean the next non-zero term here. So that's what our sine of x is going to look like. Now, if you write this in sigma notation, using sigma notation, we're going to get sine of x is going to be a summation. And we'll start with n equals 0 to infinity. Notice that we're only looking at odd powers. Of x here. But there's also a sign change mechanism that we have to keep in mind. So we'll have negative 1 raised to the nth power, and that'll be our sign change mechanism. But notice that we're going to have x always raised to an odd power, so we'll use 2n plus 1 to represent that odd number that x is raised to. And then if you think about it, the number that you see in the denominator, for example, the 3 factorial matches up with this x to the third. 5 factorial matches up with x to the fifth. 7 factorial with x to the seventh. So this x to the 2n plus 1 is always going to be over 2n plus 1 factorial, because the number down here on the bottom is going to match up with the number that you have as your power of x. And so we could actually show that this is going to converge for all real x. And so now you've got your Maclaurin series for sine of x. Now, there are many, many different series that we could use as examples for sure. But the next one I'm going to show you is going to be the Maclaurin series for cosine of x. So Maclaurin series for cosine of x is next. Now, over here, we see this familiar idea that if our function is f of x equals sine x, then its derivative is the cosine of x. But we have a representation for the sine of x right here. So you might say, well, is it okay for us to differentiate this term by term, and would that give us a Maclaurin series for the cosine of x? And the answer to that is yes. That absolutely does work. And so cosine of x is going to be the derivative with respect to x of sine x. But we know that sine x has a Maclaurin series representation like this. So you're going to have x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so forth. Now you might ask, could we go ahead and approach this problem the same way we did here? And the answer is absolutely. Yes, we could. But since we already have a representation for sine x in terms of Maclaurin series, might as well just go ahead and use that. And so our cosine of x is going to equal, and we'll go term by term. Take the derivative of x, and you get 1. Take the derivative of negative x cubed over 3 factorial, you're going to get a negative 3x squared over 3 factorial. Derivative of x to the fifth over 5 factorial is 5x to the fourth over 5 factorial. Derivative of negative x to the seventh over 7 factorial, negative 7x to the sixth over 7 factorial, and this just keeps going on and on. But this is not how we're going to leave our representation. You see, cosine of x is equal to 1 minus, and if you take 3 over 3 factorial, well, remember, 3 over 3 factorial is the same as 3 over 3 times 2 times 1. So the 3's will reduce out, leaving you with 2 factorial on the bottom. So you'll have a minus x squared over 2 factorial here. Now if I take 5 over 5 factorial, 5 over 5 factorial looks like this, but the 5's will reduce out, leaving you with a 4 factorial on the bottom. So the next part you'll have x to the fourth over 4 factorial. And in a similar fashion, the 7 that you have up top will reduce with the 7 that's part of 7 factorial. And you'll have a minus x to the sixth over 6 factorial. So you get a nice representation here for cosine of x. And in general, what will happen is we'll take a look at differentiating the x to the 2n plus 1 over 2n plus 1 factorial. Well, if you differentiate x to the 2n plus 1 over 2n plus 1 factorial, then what you're going to get from that is a 2n plus 1 times x to the 2n over 2n plus 1 factorial. 2n plus 1 that you have here will reduce with a factor of 2n plus 1 that gets produced at the bottom. You'll have an x to the 2n over 2n factorial. So that means that we can represent our cosine of x as a summation n equals 0 to infinity. We still have the sign change mechanism, so we don't want to forget about that. But we'll have a negative 1 raised to the n, and then times x to the 2n over 2n factorial. So that's our Maclaurin series for cosine of x. And we got it from differentiating the Maclaurin series for sine x, which we see actually is valid for all real x. And so this will also be valid for all real x. All right. Now, let's say that you want to find Maclaurin series. For x times cosine of x. Now that's not going to be too bad at all, especially since we already have Maclaurin series representation for cosine of x. And so, x cosine of x is going to be equal to x times, and we can write this representation down. And so when you multiply through by x times y gives you x times negative x squared over 2 factorial gives you a negative x cubed over 2 factorial. X times this will give you x to the 5th over 4 factorial. And then we'll have minus x to the 7th over 6 factorial, and so forth. So basically, each of the terms that you have here would simply get multiplied by x. And that's going to kick the exponent of x up by 1, which means that x cosine x, same thing as summation n equals 0 to infinity, negative 1 to the n, times x to the 2n plus 1 over 2n factorial. So it's kind of neat that we're able to figure out the Maclaurin series, relatively easily for x cosine x, based on the fact that we figure out the Maclaurin series for cosine x, which in turn was based on the Maclaurin series for sine x that we established. Alright, so this time we're going to represent f of x equals sine x. As the sum of its Taylor series. Centered at pi over 3. Now, if we take a look at our solution here, we're going to need to know what's going on with f. We know f of x is equal to the sine of x. And we'll take a look at first few derivatives here. So same list we had not too long ago, because after all we are dealing with sine x yet again. It's just that this time, instead of evaluating all these different functions at x equals 0, we're going to do so at x equals pi over 3. And so if we take a look at f of pi over 3, that's the same thing as the sine of pi over 3. And that's going to be square root of 3 over 2. F prime of pi over 3 is cosine pi over 3. And that's equal to 1/2. F double prime of pi over 3 is negative sine pi over 3, which is negative square root of 3 over 2. And if we take a look at the third derivative of f at pi over 3, we get a negative cosine pi over 3, which is negative 1/2. And these values are just going to cycle through. So for example, your fourth derivative of f at pi over 3 is going to be sine pi over 3, which is the same thing we got from f of pi over 3 itself. And so we got root 3 over 2. And so our sine of x is equal to, well, keep in mind what it is that we're going to get here. For the Taylor series, centered at pi over 3, first term is f of pi over 3, and then we're going to have f prime of pi over 3 times x minus pi over 3. And then we'll have f double prime of pi over 3 over 2 factorial times x minus pi over 3 squared, plus f triple prime pi over 3 over 3 factorial times x minus pi over 3 cubed. And it just keeps going on and on. And so we take a look and see that this sine of x is equal to, you got your f of pi over 3, which is square root of 3 over 2. Plus f prime of pi over 3, which is 1/2, times x minus pi over 3. Then we'll have a plus f double prime pi over 3 over 2 factorial times x minus pi over 3 raised to the second power. But your f double prime of pi over 3 is negative root 3 over 2. So if you take negative root 3 over 2, it's going to take negative root 3 over 2. You put that over 2 factorial. Another way you could write this is negative square root of 3 over 2 times 2 factorial. That's just a different way to represent it. And so I think that's how I'm going to do it here. So minus square root of 3 over 2 times 2 factorial times x minus pi over 3 squared. And then your f triple prime of pi over 3 is going to be negative 1/2. That's over 3 factorial. So you take negative 1/2 over 3 factorial. We'll write that as a negative 1 over 2 times 3 factorial. And that'll be times our x minus pi over 3 raised to the third. But notice here that when you take your even powers of x minus pi over 3, you're going to have some sort of root 3 over 2. Maybe it's positive, maybe it's negative. And then you're going to have a factorial down here. This number will match up with the power you see here that x minus pi over 3 is raised to. And then for your odd powers of x minus pi over 3, you'll have some sort of 1/2, maybe a half, maybe a negative 1/2. And then the factorials you have, this is in the case 3 factorial, this 3 is going to match up with the 3 that x minus pi over 3 is raised to. Technically, I've got a 1 over 2 times 1 factorial, and the 1 would match up with the first power that x minus pi over 3 is raised to. And so we could actually write this sine of x as the sum of two different summations. So if you think about that, you've got one summation that's going to handle the even powers of x minus pi over 3, and another summation that handles the odd powers of x minus pi over 3. Now, if you take a look at the even powers of x minus pi over 3, you'll have a root 3 over 2, you'll have a negative root 3 over 2 times 2 factorial. Next time, if you were to take a look at the next term, you'd have a positive root 3 over 2 times 4 factorial times x minus pi over 3 raised to the 4th. So if you think about that for a moment, what you're going to find is that these even powers of x minus pi over 3 can be included in the following sum. You'll have summation n equals 0 to infinity. You'll have negative 1 to the n, because there is a sign change mechanism every time. But you're always going to have this square root of 3 up top, 2 on the bottom, because you're going to have a root 3 over 2 showing up. But then you'll have that multiplied by your, it's actually going to be 2n factorial. And then this will be times x minus pi over 3 raised to the 2n. So you might say, why 2n? Well, it's 2n because you're always dealing with even powers of x minus pi over 3 for this sum. And 2n is an even integer whenever n is an integer. So if you take a look at n equals 0, negative 1 to the 0 gives you 1. You'll have a root 3 over 2. 2 times 0, 0. 0 factorial is 1. X minus pi over 3 raised to the 2 times 0. Okay, so when n equals 0, you get root 3 over 2, precisely what's showing up here. Then if n is equal to 1, you'll have negative 1 raised to the first power, that's negative 1. You'll have a square root of 3 over 2 times, well, 2 times 1 gives you 2, so 2 factorial. And then x minus pi over 3 raised to the 2 times 1, it's raised to the second power. This matches up with what we're seeing here. So we have this summation, but I'm going to try to condense this a little bit because I want to try to fit the other sum on the same line. So let's see here. We'll get it's root 3 over 2 times 2n factorial, x minus pi over 3 raised to the 2n. But then you might say, well, what about all the odd powers of x minus pi over 3? Well, that would include terms like this, and so forth. Instead of getting a root 3 over 2, you're going to have some sort of 1/2. Okay, well, that's fine. You're also going to have the sign change mechanism. If this is positive, this is negative, the next one will be positive. And so what we'll get is a negative 1 raised to the n. So we're starting with positive. And then what we're going to have is a 1 over And then we'll have a 2. That's where your 1/2 comes in. But then, notice, powers are odd, and notice 3 factorial here, the 3 matches up with the 3 there. So you're going to have a 2n plus 1 factorial. That's x minus pi over 3 raised to the 2n plus 1. So almost enough room. Let's try this one more time. So once again, 1 over 2 times 2n plus 1 factorial. It's x minus pi over 3 raised to the 2n plus 1. All right. So kind of a nasty looking representation, but it works. And in fact, you can verify that you're picking up the odd powers of x minus pi over 3. If n is equal to 0, negative 1 to the 0 gives you 1. 1 over 2 times 2 times 0 plus 1, that's 1 factorial, still 1. There's x minus pi over 3 raised to the 2 times 0 plus 1 is raised to the first. This matches up with that. And if you have n equals 1, negative 1 to the first gives you negative 1. 1 over 2 times. 2 times 1 gives you 2, plus 1 gives you 3. So 2 times 3 factorial. Times x minus pi over 3 raised to the 2 times 1 plus 1 is raised to the third. This matches up with that. And they'll continue to match up as you increase n.